Okay, some of you asked about certain thing, about the distributions of, say, the sample variance. Now, remember, everything that comes from the sample, when you do your calculations based on a formula, which is the formula does not involve any unknown parameters. That means actually you can calculate it if you collect the sample. So the formula is, you can think of it as the formula is before you collect the sample. And this is the expressions that you are going to substitute your sample once you have collected it into the formula. And this formula is called a statistic, I mean, without the S at the end. So this is basically a random variable because it depends on the actual sample that you collect. And if you repeat the same sampling method, you will collect a different set of n numbers. So that is where the randomness will come. For example, you ask 10 people's opinion about they like a certain kind of bubble tea. If you ask another 10 people, then you don't expect you will have the same answers, all right? The same, even the proportion might change. Now, so this is where the point is. I wanted to, because I want to relate other things, so that's why I'm thinking of more than one sample. So I have one population, and this is with mean mu, because I need it. Suppose x1 up to xn represent a random sample of size n taken from this population 1. And I also have the corresponding random sample of size m. It doesn't have to be equal in the size. Represents another random sample taken from population 2. So depending on your interest, we might have different kind. For example, we are interested in the sample mean because the sample mean will be a reflection of the population mean. And that is actually why you collect the sample in the first place, because you wanted to know about the population mean. So you are going to use the sample mean as an estimation for the population mean mu here. But sometimes you may not be interested in the mean of the population, but you are more interested in the variations of the populations. For example, if you are doing some manufacturing, as long as you know your machine has been set at the right place where it will give you the right mean, the specification, but you don't want the variations to exceed a certain amount because that is crucial for your quality control. So you wanted to estimate the variance in population 1. And the version that we are using is using the sample variance. All right, so we will use this to estimate the variance of the population 1. So that would be another quantity that we use. So this will be another statistic. So this statistic is to investigate the variance of population 1. And this statistic is for investigating or estimating the mean mu. They serve different purposes. And here, this is somewhere, okay, most of the time mu is not known, but this is not a statistic now, so I should correct myself. This is not a statistic. It is going to be used for hypothesis testing or for other purposes or confidence interval. So for hypothesis testing, the mu will be substituted by the null hypothesis, so it would be a statistic then, all right? So my point is to illustrate, sometimes we use more than one formula. For example, the x bar for my numerator, but then I use the s. S would be just the square root of this quantity. I have a subscript because I wanted to emphasize it is coming from population 1, and subscript y to emphasize that it is coming from population 2. So this is another quantity that we are interested. Another quantity that we are interested that will come again in our comparing the variances of the two populations, and one of the crucial quantity would be Sx squared and then Sy squared. So basically what I'm trying to say is, depending on your objective, you will create a corresponding expressions from your sample or from more than one sample to and use the sample's values to give you some sort of an indications of whatever the underlying population's parameters are. Now, but the thing that I wanted to emphasize here is that these random variables are random. So it itself will have its own distributions. Now this is the R code for the things that I'm going to demonstrate. If you are interested, I'll let you take a. Later on you can take a photo of it. Okay, so I wanted to illustrate this thing. Now in R, when we put the hash sign in front, it will comment out the line. So this will not be computed. So so here, let me mention what I'm doing here. So what I'm doing here, R stands for random. So stand for generating random numbers from something. This something, the stem of the distribution is called uniform. So R recognize UNIF is coming from uniform. The size would be indicated by the word 4, by the number 4, because I'm going to draw 4 numbers from the uniform distribution. But uniform distribution needs to be specified where the start point and the end point. So the start point is 0, the end point is 1. Now, so when I draw 4 numbers from it, so I can take a look. All right. So these are the 4 numbers that I pick. Another thing is now I'm interested to compute the mean of this 4 number. This is now will be our sample mean. But of course now this sample mean, we usually call it a realization because we actually draw the sample now, and so we are using the concrete numbers that we draw and compute the mean. Okay, and we can also calculate the sample. Okay, so this is measuring the deviations. So they would subtract here. This is a number. This is a list. So they would subtract from the list each member each from this number. All right, so I can let you have a look. All right, so they basically subtract each of the number from this. And now the sample variance is to square all the deviations. All right, and now I have to take the average. Somehow we are interested in n-1, not in n itself, all right, for some good reason. So we divide by 3, and I haven't summed it. So one way is to sum this. All right, so this would be the number that I would get, okay. Now this is only pertaining to one such act of sampling. Okay, so I'm going to do it for 10,000 times, meaning that one of you will draw 4 numbers from a uniform distribution, then another of you would draw another 4 numbers, and so on and so forth. So each one will come up with your own sample variance. So altogether, I will have 10,000 sample variance values. And so I can do a plot of the distributions because your 10,000 numbers might vary a bit. All right. Now, okay. So what I do is I create a list of, okay. So this is going to be where I'm going to store my sample values in. So I make sure I clean up the memory. So I put everything to 0 first. And then now this is a loop. Okay, so basically I'm repeating what I just did, but 10,000 times. And then each time, the kth time, I store the value into the address k, all right? Okay, so you can see this is really fast, less than a second. And so now this is where the sample variance is, because it is n minus 1 times the sample variance over sigma square. That is the distribution that we are interested. So n minus 1 is 3. And the variance, that is, we are dividing, is 1 over 12. So I have, the 12 will come up to the numerator. So I will have 36. So that is now I have to multiply my numbers by 36. This is, again, will take almost no time. And now I can do a histogram. Now, if you let out, okay, I want R to plot a histogram, and now I want it to have 40 bricks. I mean, basically 40 points. You can specify how many bricks, and you have a little bit more elaborate. You actually can even vary the, each individual bean size, but you have to tell it, all right? And somehow I have to tell the histogram how high it is. If you don't say this, and if you don't say this, the R would, by default, think of the best things for you, all right? So they would divide it into some arbitrary way. I think they have some rules behind. And then the limit, they would try to make sure the histogram take up most of the space. For some purposes that I'm going to do, I don't want it to take up too much space because I want to plot the chi-square curve later on. When I say frequency equal to false, it means that if you don't say it, the default would be actually counting the actual frequency, counting how many times out of 10,000 that you will have the number that you get fall inside a bin. So they would give you an absolute number rather than a relative number. So I want a relative number, all right, because I wanted to have the proportion. So this is how it looks like. And now I want to fit a chi-square curve. So first I have to do something here. All right. So I divide my x-axis from 0 to 12, and then I divide into 1,000 little points. So, okay. And then I evaluate the density function. I will explain to you in a minute. Okay, so now the stem of the distribution that I'm interested in is chi-square. So this is the R name for it, chi-sq. So it is suggestive. And then I'm interested in the density curve. So I have the D here. So to evaluate the probability density function of the chi-square at that particular point. And that particular point is chosen from a point in this list, all right? So I basically, for each point in the list T, I evaluate the density function. All right, so I now have 1,000 points, and I wanted to draw the curve now. I want the curve to be drawn on top of this graph. So I will take it as the main plot. Anything else would be added into it. So there is, if you just want to plot the curve, you can have a plot command, but then this thing will disappear. Now, if you use RStudio, there is an advantage of RStudio, and it would this plot will not disappear. It would be saved at the background. But if you are using just the R in this form, then this plot will disappear before it disappears, you can come here and then you can save it in whatever form that you want for the plot. But you have to do it before you do the next thing. But now I want to keep this as the main curve. And so I'm going to overlay what I plot, what I do for the density curve on top of it. So I want the curve to be blue in color. So this is the blue color. And so this is where it is. So it is an illustration of how the underlying distribution is close to a uniform, close to a chi-square distribution. Now this is not quite correct. You can see the fit is rather not so nice. It is because the underlying, the chi-square distribution is assuming the population that I'm drawing is normal. But now I'm drawing it from a uniform, all right? Okay, so, but the deviation is not too bad because I've mentioned that the central limit theorem actually works quite quickly for the uniform distribution because of the symmetry of the distribution. So if you, I'm not going to spend time on this, but if you are interested, you can actually change it to normal, all right? So this is what the code looks like. I think this is, anyway. Well, I think it's a little bit faint, but I think you probably get the point here. I might have this. Oh no, I didn't save it here. All right. Okay. Anyway, so that is the point I'm making. So you probably can tell I like this illustration a lot. This is actually illustrating for the sample mean. What I just did is for the sample variance. So we are just doing something similar. All right. So this is just an illustration. As long as you are able to draw something from the population in R, then depending on what expressions you want, and then you can repeat the drawing many times, and then you will have a good idea of what the distribution looks like, all right? So this is what we call the sampling distribution. So here you can think of this as the sampling distribution of the sample mean for size 5 if the underlying population is uniform, and if this is exponential, and if this is normal. All right? What I have illustrated is the sample variance. Okay, so I think I need to speed up a little bit. I'm going to skip some of them whenever I come to a pair sample t-test, but I will briefly let you have some idea what the trick was there. We have talked about this. For the chi-square T distribution, F distribution, you don't need to know the formula for the density functions. All right. We are mostly using it as a user. Another thing that I want to emphasize again is if you are relying on the table that we provide you, the table is always using the upper tail. All right. So the alpha here, suppose it is 5%, 0.05, then it would be 5% from the upper tail. And usually people call it 95% because they think from the left, all right? Okay, so this is the chi distribution, chi-square. The chi-square distribution is actually related to the sample variance, all right? And in my simulation that I just shown you, this is the expression that I'm illustrating. So n were equal to 4 at that time, and then sigma square is 1 over 12, so that's why I have 36 in the simulation there. Okay, and now I want to show you the t-distribution. One of the main curve, okay, the t-distribution in our situations comes from here, comes from a statistics that is a fraction. The numerator is coming from a normal distribution, and then the denominator is the square root of normalized chi-square. Okay, U is chi-square of degree of freedom n, so you think of dividing by n is a way of normalizing it. All right. Again, you don't need to bother about the density function. Not many of us remember it. This is a little bit of the history of the t-distribution. Sometimes people call it students' t-distribution, and this is where the history was. And again, the emphasis is now this number, this is the quantile, all right, more or less the quantile is counting from the right-hand side, all right? So the area is alpha, but this is bigger than this number, so it means if Tn alpha is this particular number on the right-hand side of the distributions, then the area covered by it is alpha. The n match with the degree of freedom here, so you need to do that. All right, and this is an illustration, so make sure you know how to get this number, all right, from the table, all right. R can also do that. So this is a more convenient thing to do because most of the time you can use software only when during our exam for this particular case you need to use the table. Again, if you use a graphic calculator, you can ignore the table. So this is how we get this. All right, and actually this table is, I think we reproduced this table ourselves. In the past, it took a lot of manpower to come up with this kind of table. All right, you can see infinity. Yes, okay, it is not very clear here. The infinity will correspond to the normal distribution. All right, and the number is 0.674. And you can see the number is getting closer and closer to 0.74. So when the t-distribution, the degree of freedom, is increasing, getting larger and larger, it is very close to the normal distribution. And the usual rule of thumb would be think of either 30, but you will see 30 is a little bit off. I mean, okay. And then another rule of thumb is 60. You will get confused. I mean, 60 is, of course, much better. It is 0.679. I mean, so you will see in the past, computing power is very limited. So people resort to all different kind of rule of thumb and all this, but this is rather unnecessary nowadays. Okay, again, you don't even need to remember this. I don't quite remember this too. Anyway, the mean is 0. This is useful because the t-distribution is also symmetric. So when people say it's a bell curve, this is actually very subjective because if I give you a t-curve, even for degree of freedom, say 6, you can't really tell from your eye whether it's a bell curve, I mean the normal distribution, or a t-curve, all right? So, but you don't take this very seriously. All right, so this is the rule of thumb spelled out in this slide, so N30. But again, in actual work, you can just take the t-distribution because it can be computed quite easily. So this is actually, you can forget about this too. The curve is interesting because the blue curve is where the bell curve is. The color curve, the green and the solid curves correspond to the t-distribution, and they have fatter tail, basically. Because of the way we plot it, we plot the entire curve, so you may not see the difference. But if I only plot from 2 onward, you will see there is a substantial difference between the solid curve and the ideal dotted curve, which is the normal. So the correction is actually necessary, especially for some experiments where because of ethics or because or other limited resources, people don't do a lot of experiments. So they only do 5. Say in microarray, they only do it 4 or 5 for each set of conditions. So it is expensive. So yeah. All right. So this is the statistic that we are testing. The reason why we are doing this is the following. We will mention it when we come to it, but this is the reason. Very often we are interested in the mu, so we assume the population is mean mu and sigma square. Here, this is our interest, but under these conditions, interest is unknown to us. But sigma square is also unknown to us. All right, this is the most sensible thing, unless something that has been in production for a long time that you can assume something is known, right? Okay, suppose it's known. Now, if our interest is mu, so in a lot of situations, we are interested to compute this. All right, and this would be a normal distribution. All right, but now we can only afford one unknown here so this is one unknown. So that means somehow we have to replace the unknown by the one that we are estimating. All right, so this is use this as to estimate this. But the introduction of a random variable instead of a constant will change the distribution. And so this is after the hard work of William Gossett. So this is a t-distribution of degree of freedom n-1. All right. So that is, and of course when n is really large, then this is approximately normal as well. So there is not much change, all right? But this is only provided that it is the n is large. Okay, this will come up, all right, in the next chapters or the chapter 7. All right, so we are talking about this. So we have to replace the sigma by the sample standard deviations. So we have this, okay, and so this is just explaining what's going on here. And now, so we are doing this. This is how the things come about, and also why people are interested in doing the normalization is because things cancel out nicely. So this is a neater expressions. Okay, so this explains why we are doing here. Okay, it disappeared anyway. Okay, the result is true for all n, though it is mainly used in cases where n is small. small here refers to less than 30. This is because for n large, the t-distribution is getting closer and closer to the normal distribution. Okay, so a midterm test. The lecturer of a class announced that the mean score of the midterm is 16 out of 30. A student doubts it, so he randomly chose 5 classmates and asked them for their scores. So this is something that you can do too. Should the student believe the mean score is 16, assume the scores are approximately normally distributed. All right. So usually the test score is normally distributed if the test consists of many small parts and there is no one major part. So something like the central limit theorem will kick in. So based on the numbers, so this is the actual numbers from the sampling. So I can calculate the sample mean, and I can now I assume the mean of the population is 16. But since in the example we were not told by the lecturer what is the population mean here, so I can only resort to the sample standard deviations. So I plug in everything there. All right. So this is a standard applications. So I will have this. So I have 5.26, and based on the T table, if I use 99.5, that means 0.5%. This is 4.604. But this, so if you think of the curve in this way, so this is the T distribution. So from the table, the best that you can have is 0.5. So this is a 0.5%, and this is 4 point something, 4.604. But the number you get is actually on the right-hand side, which is 5.24, 5.26. So this number is, that means in order to have the actual mean 16 that the lecturer told you about it, then it is very highly unlikely, because it would be even less than 0.5% of the time that you have such a large statistic value here. Okay, so so this is actually give you a glimpse of the hypothesis testing thinking. All right. So of course it didn't draw any conclusion here. All right. So should the student believe him based on his findings? I would say no. All right, because it's very unlikely. But that would put the lecturer in a very bad light. So he's probably lying. A manufacturer of light bulbs claims that his light bulbs will burn on the average of 500 hours. To maintain this average, he tests 25 bulbs each month. So again, we can compute this, all right, and then look for whether it falls between this. Okay, this represents 5% on the right, the upper tail, and because the t-distribution is symmetric, so if you take the negative value of this number, it would be another 5% of this little tail. So what it means is inside would be 90%. So this is actually what he's doing. All right. So what conclusion should he should be drawn from a sample of that has mean this and standard deviation of this? So now we plug everything in. All right, and it turns out to be 2.2. Okay. So maybe I draw a little diagram based on this. So this is highly exaggerated. This is a T25, and we want this to be 5%, and we also want this size to be 5%. Since the table always gives us the right upper tail, so this is this can come from the table. All right, so this is 1.711. And we make use of the fact that the T distribution is symmetric. So in order for it to be 5%, this number would be the negative of this. All right, and what is the, for this particular month, the sample, the T-score of this is 2.25. Okay, so it is, if you are using this 10% thing, now the light bulb is likely to have longer than 500 hours, all right? Okay, because we are testing whether it is 500 hours. So it is on the 500, more than 500 hours. So this should be safe, at least from legal consequence. I mean, if you say the bulb is guaranteed to have 500 hours and on the average 518, you are safe. Okay, but of course it might affect the sale, and the bulbs burn longer, so you can't sell as many. So this is the situation. So this is where the thinking comes about. So the F distribution is the distribution of the ratio of two estimates of variance. It is used to compute probability values in the analysis of variance. Something that I think we are not going to do. So the analysis of variance called ANOVA, A-N-O-V-A. You come across this term very often. This is an extension of a two sample t-test. If you have more than two samples, comparing more than two populations, then now you have three sample or three populations that you want to compare, or you have four and so on. So the analysis of variance, ANOVA, A-N-O-V-A, is doing the same thing as in the two sample t-test. But we are not going to go through this. So a F distribution, basically, again, forget about the density functions. This is, again, not important. The important thing is where the F distribution comes about. It comes from the ratio of two normalized chi-square distribution. All right? So U is a chi-square distribution of n1 degree of freedom. And so you normalize it. So it is U over n1. And then V over n2 is the other chi-square. Now we need we need quite a strong assumption. We need the assumption that U and V are independent. All right? But the independence will come from if I draw the two samples, one from population 1 and one from population 2, draw them in an independent manner. I mean, I draw this, blindfolded, and I draw it blindfolded, all right? But this may not be the case in a lot of medical research. People do something like a case and a control, so they might match the first one that you draw with the first one that you draw from the other population. So independence may be lost over there, all right? Okay, now where is our applications? So we have random samples of sizes N1, N2 drawn from two normal populations. We do assume normal populations, but if the sizes are big enough, the central limit theorem say, these assumptions can't be too off, all right? So, so U equal to this. Now this is your sample variance. And in an earlier slide, we have to multiply this by N1 minus 1. So, and then divided back by its sample population variance. And this will be a chi-square. And you have to do so for the other samples. And this has to be replaced by the variance of the other populations. Okay, so this is how the F distribution will appear. And now the F distribution is a bit tricky because you have to keep track of two numbers. The T distribution, you have to keep track of one degree of freedom. What is the degree of freedom of this T distribution? The chi-square, you also have 1 degree of freedom that you have to keep track. But the F distribution being the ratio of two essentially chi-square, so you have 1 degree of freedom from the numerator and then another degrees of freedom from the denominator. So we have to have two numbers to track it. Now, the convention is the first number refers to the numerator. The second number refers to the denominator. So if you switch the order, then it would not be right, all right? Okay. There is one nice thing about this. The F distribution, if it is coming from the ratio of two chi-square, normalized chi-square, degrees of freedom n, and then the denominator is m, 1 over f would be interchanging the denominator and the numerator. So the degrees of freedom would be swapped, all right, would be m and n, all right. So that is the reason, because basically the f is the ratio of two chi-square. The first number tracks the degree of freedom of the numerator, and this is the denominator. So when you take the reciprocal of the F distribution, then the degrees of freedom will be interchanged. Okay, again, this is our notation, F n1, n2, alpha. So n1, n2 refers to the degrees of freedom of the F distribution, and the alpha corresponds to the area that you want, but it has to be from the right-hand side in our notations. So maybe I'll let you try it, looking it up from the table I think I've uploaded. So now this is a little bit tricky. So you have to, in our table, I think we put the first degree of freedom of the F distribution as the rows, and then the columns corresponds to a different degree of freedom of the denominator. And then, so 0.05 would be one, for 5% would be one table, because we have to exhaust the different n and different m, all right? And then another table would be 0.005 and so on, all right? So you will see there are more tables because we just have one more degree of freedom in the distribution. Okay, I think this is asking you to test this. Now, so I let you figure it out, because this is testing not only just looking it up from the table, but also to see the degrees of freedom is being swapped. So there is a reciprocal relationship there, all right? So you try it, and we have this. Okay, this will come up in our hypothesis testing. Let S1 square and S2 square will be the sample variances of independent random samples of sizes 25 and 31, drawn from a normal populations with degrees of freedom with variances 10 and 15 respectively. So I'm interested to calculate this, all right? So now we have to re-express this. This is almost the form of a F distribution, because it is actually the ratio of two normalized chi-square. So we have to do something about this first, all right? And then when we have the F distribution come in, then we look it up in the table. So this is how it comes about. So if I divide by 10 in this manner, and then divide this by 15, then this will be a F distributions. So in other words, if I were to, so I can't use this as it is to look it up under the table, but I have to transform this in this form. So that means I have to divide this by 10 and 15. So I have to basically multiply this by 15 over 10. And so I have to do the same thing for my right-hand side of the inequality. Okay, so anyway, this simplified to be 1.89, and it worked out to be 5%. Now, these numbers are really deliberately chosen, Y25 and 31. It is because we have the table for 24 and 30 for you. All right, and why is this number 1.89? This is, or 1.26 in here. It is because we want to produce 1.89, and with 1.89, you can see it in the table. All right, but sometimes the number you get, for example, if it is 1.92, you don't see it in the table, then you just take an approximation of this. So using the table has this drawback, but using software, you would be able to compute a more precise percentage here. All right. So in fact, this is the thing here. So this is not exactly 5%, but a little bit less than 5%. Okay. Yes.
Just a quick question. In the tutorial, when they're going over F distributions,
yes.
One of them mentioned using the chi-square table. Can you use the chi-square table for F distributions, or only the F table?
Okay, if now the degree of freedom is m and n, right? So if one of them is 1, then it is actually a chi-square in some way. Because, oh no. I don't know how to answer you. So I'll answer you on Tuesday. So which tutorial was that? I mean, 10. Okay. So I think it might be good to have a break here. I will quickly go through this. Yeah. Looks like we have to use the whole week 13. Yeah. So it's the bad news. Okay, we are into chapter 6. Statistics actually has a number of facets depending on the applications. Sometimes we are interested in estimating the unknown, and the estimation can be thought of either as a point estimate, or sometimes we are not so bothered about a very sharp estimation, give a number, but rather we are interested in giving an interval, so that this interval has a very high confidence that it would contain the mean. Now I change the word for high confidence rather than probability, because I will explain a little bit later. Because once a sample is chosen, then the confidence interval that you constructed will either contain it or will not contain it. Okay, I think we have some plot to illustrate this point. All right. So the introduction here. So we are interested in the parameter. So what it says is that in a lot of applied work, some experience give us the idea that the curve is of a certain shape. And so we sort of know, or we feel a bit comfortable to assume the density function is of a certain form. The only thing that we are not sure is that what is the parameter for that. For example, you know the curve is decreasing like exponential decrease, but you do not know what the rate is, all right? So we want to estimate the rate of the decrease. So we are willing to assume it is exponential curve. Or if we look at the density curve, and now of course you don't have the density curve, it is also another statistical procedures. But let's say if you use a histogram, and if your histogram suggests sort of like a bell shape kind of thing, then you might want to use a normal distribution to fit it. But for the normal distribution, you do not know the mean and you do not know the variance, because once you know these two numbers, which we call parameters, then you will be able to fit the data. So this parameter is something that is what we know. So an estimator is a rule. So here, or expressed as a formula that tells us how to calculate an estimate based on information in the sample. Now, maybe I emphasize this. Estimator is a formula, all right? Whereas that formula actually is conceived even before you collect the actual sample. But the estimate is after you collected the sample, and then you know the individual values, and then you plug in the individual values into this formula, and so you will come up with a number. And this is what we call an estimate. Now, if we have more than one of you, say for example, everyone here, each one of us collect our own sample, and then we use the same estimator to the same formula, so we will come up with different numbers, all right? And if the estimation is good, it should more or less center around the unknown. So this is something that occupied a lot of statisticians in the last century. Okay, in this talk we'll look at two types of estimations. One is called the point estimation, and then the other is called an interval estimations. So based on sample data, a single number, so this is the single number that you calculate based on the estimator, based on the formula, and you have a number, and this number is called a point estimate. Or you will actually want to have an interval based on the sample data. I want to have two numbers, okay? One is the smaller number, one is the bigger numbers, and this will give us an interval. And we are hoping that this interval will, most of the time, track the unknown parameter, all right? So let us first discuss the idea of point estimation. This is awful here, okay. But what it says is that a formula, so this uppercase of theta, and now this is, get a bit of time to get used to. All right, so first thing, think of the big theta, okay. This guy represents the uppercase of our Greek word, Greek letter theta, okay. This is the uppercase, this is the lowercase. And I have a hat, means it's an estimator. It's not the real thing. I mean, it's something that I base on my estimator based on my sample to estimate. The idea is that when I have without the hat, it's the real quantity. And with the hat, it means I have some way to estimate this, okay? And this is a formula. The formula involves the individual sample values. So this is the meaning here, all right? And this is what we call a statistics, okay? Provided that this formula does not involve any unknown quantity, all right? Because if you involve any unknown quantity other than your samples, then in your calculations, the final answer will involve the unknown quantity. And so you can't have a number, all right? So a statistic is a function of the random sample, function in the sense of a rule or the formula that does not depend on any unknown parameters. So the word statistic has a very specific meaning here. For example, this is what we call the sample mean. All right, and there are also occasions that I'm interested in the maximum of the sample. For example, I'm interested in building a dam for my river, and I have the previous, highest water level, and I'm interested, of course, not in the average, because I'm interested in the highest, among the previous, say, n months or n years, and I'm interested in this. Now, there is one very interesting problem, that actually is called German tank estimation. You can Google it. The Allies captured some of the tank by the German, and they wanted to have an idea how many tanks actually the German have produced during the Second World War. All right, so if you Google it, you will find information. And the estimator is based on the maximum, because the tanks that they captured have some serial number. Okay, of course, there are many serial numbers that they can find, but some they suspect it has to do with the serial number of the tank, the cave tank that they have produced. So they wanted to have some idea how many tanks that the Germans have produced. This is a very important information for the ally. Another one is this will be a statistic. So if we are measuring the deviations of your sample value from a number mu, now this will be a statistic if mu is known. If mu is unknown, then this is not a statistic. So this is a good example, because if you imagine you collect a sample, and if your mu is not known, no way you can proceed to compute this number. All right. So this will not be qualified as a statistics. But if mu were known, then this is okay, because you can plug in the value of mu that you know into this formula. So point estimate of mean mu. Suppose the parameter of interest is mu, the population mean, and suppose we have the following data, a random sample which is x1 up to xn. The statistic that one uses to obtain the point estimate is called an estimator. An estimator for mu is x bar. Now, this is beyond the scope here. It turned out the sample mean has a lot of optimal property to estimate the population mean mu. And so this is almost the default estimator for the population. Now, of course, you can also just use, for the sake of argument, just use the first number that you use, to estimate the mean mu, ignoring the other n-1 numbers. But of course, this is not a sensible thing, because if you only use one and ignore the others, why should you collect the others in the first place, right? Or you can just take the average of a few of them, not the entire average. So again, the argument just used so that it is not sensible. And mathematically, we know that the sample mean, as we define, enjoyed many optimum properties. So we have this, and so x bar is equal to 5, so we use 5 to estimate my mu. Now, this is reiterating the point that we have mentioned a number of times. The different random samples will give different point estimates of mu, all right? But if your estimation is reasonable, and if the sample size is reasonable, they would center around the mu. But they may not be, they are unlikely to be equal to mu. Okay, this is not a statistic, so we have mentioned it. Okay, and unbiased estimator. Unbiased estimator means, just now in the simulations or in the graph that in your slide, you pick a sample of size n, you calculate the sample mean, then you repeat the procedures 10,000 times or even more, and you can find out the distribution. And from the distributions of the 10,000 number, you can find the mean again. And so what it says is that the mean of all the mean of your sample mean is equal to the population mean. It's a mouthful here. So let me just write it down. So mean of the sample mean equal to the population mean. All right. So so this is a very good property, because you will not have a systematic bias. All right. Because if it is always minus something or plus something, then you are always off. Okay. The sample median is also another good estimation of the population mean if the population distribution is symmetric. All right. So if it is not symmetric, it will be off. I mean, for example, the income distribution. If you are interested in estimating the population mean of a big corporation, of the salary, you will, if you use the median, you will be off, because a lot of corporations, a few people are being remunerated for very high salary, but most of the people, draw small salary. So one of the reasons we think of is a good estimator because of this. But there is a drawback of the sample mean. The sample mean is very much affected by extreme numbers. I mean, suppose you happen to ask the CEO of the company, and so his salary, if he wants to disclose it, then it would affect the mean a whole lot. So, so this is what we call non-robustness. The mean is not very robust. There are some ways to get around this. Of course, we won't get into it. It's what we call a trim mean. Trim the largest, a few largest number, and trim the lowest few numbers. And so we only calculate the average of the middle part. This is very much like in Olympic Games. I mean, like a number of this where the judges judge the people, say diving or some. So they actually trim out the very high score and very low score, and they only keep the middle part. All right. So this is a formula. Think of this as a formula for estimating something. Okay. Without the head is the real thing. All right, but it's unknown to us. So the expectation of this, whatever. So the example you have here is the sample mean. but it may not be the sample mean, all right? So this is the definition. Whatever things that you are using a formula to describe it, and if you were to do the simulation many, many times, on the average, it will give you back the unknown theta. Then this is called an unbiased estimator. An unbiased estimator has mean values equal to the true parameter. So if this is the true parameter, and this is an unbiased estimator, well, of course, this is the artist's impression. We are drawing the distribution of the estimator to be symmetric, all right? So it may not be symmetric. But say, if I find the mean of this curve happen to be the same as this, then this is unbiased. But if you look at this, very often, from the curve here, it suggests that this estimator is not only biased, but it will, most of the time, will be overestimate the true value, all right? So the bias estimator has the true value plus the bias, and the bias is positive here. Just like, for example, you weigh something, and if the scale is not set at 0, but is set at maybe 1 or 2, then whatever you weigh, no matter how many times you weigh, you will add 1 or 2 into your reading. So, so this is, we have, if your last chapter we have shown something like this, it is the expectation of the sample mean. You remember we take out the 1 over n in the formula, and then take expectation of term by term, and each of them will give you mu. So you have 1 over n bracket mu plus n times. So this is it. So this is something that we have shown. An unbiased estimator. This is, we don't want to spend time on this. So this is the reason why the 1 over n minus 1. Imagine if this is the other version that you use. Okay, and if this is the case, this is what we use. The expectation of S squared. So I pull out the n and multiply n minus 1 and n minus 1 here. Okay, and this would be sigma squared if I use the result in the slide. So you will be off, and the amount that you are off would be negative. So the traditional one that if you use 1 over n will always on the average, will underestimate the population variance. And the amount that you underestimate, if you take the percentage, okay, the relative error would be this. So the average, okay, and so so you will be underestimated by this amount, 1 over n, relative error, all right? Okay, so, and this is the reason why we have n minus 1. But of course, it's getting not very important when n is large. Say, for example, when n is, say, 100, then you are probably differ by 1%, all right? But depending on whether the 1% is important to you, all right? So, oh, this is already done here, all right? Okay. A1 bus at the bus stop, I think we missed out one word. I mean, A1 bus arrives at the bus stop according to a uniform distribution. The lecturer wants to estimate theta. So this morning, he randomly selected 4 students and asked their waiting time for a bus. The values are obtained. Is X bar an unbiased estimator of theta? Now, X bar is an unbiased estimator of the mean of the distribution. So, so the mean of the distribution is the center of gravity for the uniform distribution, and that would be the midpoint. So it would be theta over 2. So x bar is actually is an unbiased estimator of theta over 2. It would not be theta. So find an unbiased estimator of this. We will see the calculations. So the expectation of x bar is the same as the mean of the population. And the mean of the population is not theta, but it is theta over 2. So this is a biased estimator. But here, the expressions differ by a factor, so it can be corrected quite easily. You multiply this by 2 on both sides, so just like this. This will be one of them, all right, because this is actually how the 2 was figured out, but we prove it in retrospect, all right. Okay, so I forget about C. Is there an other unbiased estimator of theta? The answer is this. You have many of them. So you can just add the first 2, add the first one and the third one, and so on and so forth. And if I can also average 3 of them, but I have to multiply by 2. Basically, I ignore the 4th answer, all right? Many of these, they are unbiased, but somehow we feel that it doesn't quite make sense. In practice, if you only use a subset of the sample, why would you collect the whole sample in the first place, right? This is beyond us at this point, which one to choose, all right? Which one has the better quality. But I think the part C has the merit saying that unbiased estimator is not unique. You have many choices, okay? And so the next kind of questions, natural questions would be which one would be better. But we are not going to dwell into it. So now if you keep the meaning in mind, so forget about the hat for the time being, forget about the L, all right? So I just want to have a formula. The formula based on the sample, all right? The L would be something like, meaning that it's going to be my lower estimate of the number, of something, the parameter that I'm interested. Okay, and usually we will use the lower case of this Greek symbol corresponding to the unknown, so the theta. All right, the hat here is just to emphasize that it is estimation. It is based on a sample. Okay, so now instead of having just one single formula, I'm interested in coming with 2 formulas. One will give us a lower estimate, and then one will give us an upper estimate. And so as a result, this interval, this is the lower bound, this is the upper bound, will constitute an interval for which it is very likely that the unknown parameter will fall inside this. Now this is okay for saying the word probability because this is just a formula. So this is random, this is random. So this interval is random now. But once you have collected the sample, and once you have already substituted the numbers into it, so this will be a number, this will be a number. So whether the parameter theta will be inside or outside will be either with probability 0 or 1. It is either yes or either no, right? Because if you have an interval, either it contains it or it does not contain it. Okay, this is an example. This is an example of something like if someone gives you top of the head this kind of suggestions, now we are able to compute the probability of this coverage, all right? What is the probability that mu is inside here? Okay, so let me phrase it as a question rather than just this. So we will deal with it. This will be a classic case. So we'll ask what is the probability that here is in this. We assume sigma is known. Okay, otherwise this will not qualify to be a statistics. So in other words, we are interested to compute all right, so we will be interested in this. So I think it would be best to leave example 1 with these questions. Later, because we want this probability to be good, to be large most of the time, all right? And a good probability would be 95%, 90%, or 99%, yeah. Okay. Okay, so interval estimate. An interval estimate of a population parameter theta is of the form here. So this is supposed to be my lower, and suppose this is my upper one. Now this will not be always true. All right, this will only be true with a certain probability. This may not be true. All right. So I think later on we will give you some illustrations. So the idea is to give a lower confidence limit, all right? And this is based on the statistics. And I also want to have an upper confidence limit, and this is this. And this interval will constitute by the lower limit and the upper limit. And I hope that my point estimate will fall inside this interval, all right? So this is the confidence interval. And the width of the interval is this. All right. Okay, different samples will generally yield different values of theta, and thus the different values of the lower confidence limit and the upper confidence limits. So the endpoints of the interval are values corresponding to random variables. All right, and the length will also be, in some cases, it can be random. These intervals may or may not contain the parameter. This is, this is important because a lot of students, when they first learn it or in high school, they would think that with probability 0.95, that the interval you constructed, which is not random anymore, the probability of theta is falling inside this interval. Now this is not a probability statement because it is either yes or either no kind of questions here. Okay, and we want alpha usually is small, all right? So unfortunately, this is how people write, okay? But this is going to be consistent with our notation using the upper tail cutoff. So I want the alpha to be small, meaning that with very good probability, which is 1 minus alpha, the interval that we constructed, which is random, will capture the theta. All right. Suppose alpha is 5%. So what it says is that this random interval will have probability of 95% capturing the unknown. This is what you want, right? But of course, it is too wishful to think that you can achieve probability 1, all right? So no way you can do it with probability 1. Okay, now once you have computed it, so now we switch it to lowercase. So this is the difference here. So, over here, we use the uppercase, which represents a formula. And here, this is after you substitute the sample numbers that you collect into the formula, and so you get a number, okay? And so we revert back to the lowercase, but to distinguish it from the parameter, we have a hat here, all right? And this will serve as a lower estimate, and this will serve as an upper estimate. And so now we change our wording. We change it to confidence rather than the probability, all right? So, and we call this interval a confidence interval. Okay, and the coefficient, 1 minus alpha, is called the confidence coefficient or degree of confidence. So we move ourselves away from talking about probability because probability here does not make sense. All right. The endpoints are called lower and upper confidence limits. So this is to introduce the terminologies. Okay, this means that if many samples of sample size n are taken, and their confidence intervals are constructed, 1 minus alpha times 100% of this will contain the unknown parameter theta. So this is the illustrations. So in these illustrations, I have 1, 2, 3, 4, 5, 6, 7. Imagine you actually might have 10,000 of them, all right? So, okay, so if you have 10,000 of them, and if you want a 95% confidence interval, then I would expect 5% of 10,000 is what? Is 50, right? So I would expect of this 10,000 interval that I constructed, 50 of them will not contain the unknown parameter. But I can't really pinpoint which one, all right? So here, now in reality, in practice, you only calculate one confidence interval. You won't collect the sample again and again. So you might be here, okay? Or you might be here. But the confidence that you have is, unless you're very unlucky, you cannot capture the unknown parameter here, okay? But you can't be sure, all right? You can't say 95%. I would, with probability 95, this is in, but this is either in or out, all right? So the 95% refers to, if you have many of such confidence interval, 95% of this, all these intervals will capture the mean mu, all right? In the next few sessions, we will look at how confidence intervals for various cases can be derived. Because of time constraint, I'm not going to derive them, but I will just show you the intervals. All right. So now it's going to be okay. So we are dealing with normal distribution. Most of the time. Okay, and so there are many cases, mu known, sigma square unknown, mu unknown, sigma square unknown, and mu unknown, sigma square known. Of course, the remaining case, mu and sigma square are known. That is the happiest case. We don't need to do estimation, right? So now a lot of calculations, we are going to concentrate on this, all right? Because you can, if sigma square is known, what you can do is you pretend you don't know, right? You can do so. If you know it, and you can pretend you don't know it. But if you don't know it, you can't pretend you know it. All right. So that's the difference. Now, some of the cases is we pretend we know it when the sample size is large. All right. So when the sample size is large, we can pretend to know it. And also, if this is not normal, if this is questionable, then we have large sample to help us. Okay, so either we make an assumption on the population being normal, or we assume underlying thing, the sample size is large enough. So of course, it is much safer to use large sample, but resources might restrain us to use large sample. So basically, the idea of large sample is to use the central limit theorem. All right. So I guess I would just jump to this case. The others are very similar. And I believe many of you in your high school, you have done this. Okay, so this is, again, the upper tail probability, which somehow quite a number of us are using the upper tail. Okay, and this is it. All right, and this is the standardization. All right, this is because I'm using this number to represent the curve for the normal distribution, standard normal. So I have to change it back to standard normal in all my expressions. All right, so I have this. So with this as alpha over 2, what does it mean? This means this is, first of all, underlying assumption. This is a standard normal. Less than or equal to this, it means that on the right-hand side of this particular number, the area is alpha over 2. Because the thing is symmetric, less than minus of this number would also be alpha over 2 for my lower tail. So both tails will contribute area of alpha. So the middle part here now would be 1 minus alpha. All right, so this is where the picture is telling us. So because this is by the way we use the notation here, this refers to the orange color on the right-hand side is of area alpha over 2. And by symmetry of the standard normal curve, this will be alpha over 2. And this number has to be the negative of this number. And so the middle part will capture the probability of 1 minus alpha. Now, here I want to emphasize, now it's safe to talk about probability because this is just a formula. This is a random variable. I haven't substituted my sample values into it. If I substitute into it, then I will usually use a lowercase x and then with a bar on top. All right. So, okay. And now this will, because of this, we are reverting this. Okay. From here, we can solve these two inequalities to become this. All right. So, so this is the confidence interval for this one. All right. Okay. Now, having the confidence interval is something that helps us for sample size determination. Because suppose to collect one sample, one reading costs you a certain amount of money. I think I might told you the story. I mean, some graduate students were doing studying dogs about the canine tooth. They are interested in knowing how many canine teeth can they extract from the dogs. Now, of course, especially if you're dog lovers, you don't want the number to be excessive. I mean, it's hurting the dogs, I suppose. And so we wanted to know the sample size. But if the sample size is not large enough, then our scientific conclusion will not be able to stand. So there is a trade-off here. So this is how the sample size is decided. So now, okay, how do I get this? All right, so if I wanted to have this, I unfold the absolute value. So if the absolute value is less than equal to, say, 10, it means that the number is bigger than or equal to minus 10, less than or equal to 10, right? So, so that would be less than this number and bigger than the negative of this number. And so I move my mu over. Okay, later on, then I will move my mu over. Okay, so we want to estimate the error to not exceed the margin of error. So this is crucial. But you cannot expect it's only with certain probability. You can't do it for probability 1, all right? With probability 1, then you can't be certain that you will not exceed the margin of error. you only can assure that the margin of error will not be exceeded with a certain probability. Okay? Okay, so now because of this, so we are comparing, so this would be our, if this is our margin of error, okay, then this will be, okay, this is the error that we are going to be able to afford, okay, with probability 1 minus alpha. So if I choose margin of error E to be bigger than this, I can guarantee my probability would be even at least 1 minus alpha, right? Because if you choose E to be bigger than this number, so the probability will go up, okay? So this leads to this. So if you are okay with this in the argument, then now I ask the reverse questions. What would be the sample size? So my sample size would be just solving this inequality. So I move my square root n up here and move my error, margin of error down here, and then I square it. Okay? So this is the expressions of the margin of error. Now, of course, here it involves some knowledge about the sigma, the standard deviation of the of this. But this makes sense because if your margin of error is small, you expect to have more samples. I mean, you need to have more sample size. So this expression tells you that because the margin of error is in the denominator. If your variations of the population is large, again, in order to sort of have to restrict it in your averaging, again, you need to have a larger sample size to offset the large variations in the populations. Okay, so this is the expressions for that. But bear in mind, this is under few assumptions. First, we are working on normal distribution, or the sample size is reasonably big when we sort of think the central limit theorem can kick in. The second assumption would be the sigma is known. Otherwise, you can't calculate. The margin of error is given by outside, external, by your supervisor or whatever, or the problem sort of natural. Okay, so the mean of the CAP of a random sample of 36 college seniors is calculated to be this, and assume that it is from our previous studies that the standard deviation is 0.3. So we now can compute all this. All right, so this is just a very kind of, routine substituting the numbers. So 1.96 is from the table. All right, okay. And people usually approximate it to 2 because 1.96 is around 2. And that is why people are interested to use 95% very often because it is easy to remember. So we have an interval like this. Okay, in order for the error to the margin of error is 0.05, and I want it to be the 95% confidence. So my n has to be bigger than or equal to 138.3. So that means I have to use 139. So you need to have a sample size of 139. Okay. Okay, so this is similar. Now, if you remember how we handle the confidence interval, okay. Okay, so I should have skipped the one that I used. Okay, with the when sigma is not known, we are at a we have a problem. The problem would be this lower confidence limit and upper confidence limit cannot be calculated. So a way to get out of this is to replace the sigma by the sample version, so by the S here. And now, of course, the guy student T says that now is no longer accurate to use the standard normal. So you have to change it to the T distribution. So the change would be change it to S and change it to T n-1 degree of freedom and alpha over 2. All right, so this is the change. So everything else would be the same. Okay, so this is where the change is. And the change would be change the sigma by S. So everything will go through, all right? So you just change the sigma by S, the standard normal number by the t distributions. And we can also calculate okay, so this is for large N. Because for large N, this number is almost like set alpha over 2. All right, so this is, I mean, things are actually related. Okay, and so you plug it in. This is where you get it. Now, suppose you assume the sigma square is known and it is equal to 0.08. Your interval would be a bit narrower. It is because you have more certainty because your sigma square is not, you don't need to estimate your sigma square. Whereas here, your sigma square is not known to you, and so you have some uncertainty coming from the sample. And so as a result, your interval has to be a little bit bigger to offset the uncertainty. Okay, so I guess I will not go through this. I think there is some mistake in the compiling the math formula. Okay, so I will stop at here. All right. So we hope to finish it soon. This chapter. This is week 11, right? So yeah, hopefully by end of next week we should finish this chapter plus a little bit ahead of this. Then we'll try to finish it, some of this in week 13. All right. Yes. Okay. Good questions. We have actually checked everything, and I mean the other professor will upload it. So the understanding I have, he will upload it maybe by this week. I mean, so which is today. I mean, so yeah, hopefully, yeah. Yeah. Yes.